Welcome! In this video, we'll be talking about Gauss's law and electric flux. Here's what we'll be going over. If you want, you can pause now. Otherwise, let's just get started. So first, I want to talk a bit about the motivation and intuition behind Gauss's law. So, if you draw an electric field line diagram, then something you might notice is if you enclose the electric charge, the surface that you use to enclose it, there'll be 4 electric field lines going through it in this case. And no matter what surface you draw, even if your surface looks something like this, you're going to have a net 4 electric field lines coming out. In this specific case, we have 1, 2, 3, 4, 5 electric field lines coming out, but we have 1 electric field line coming in here, so the net amount of electric field lines going out is 5 minus 1 equals 4. So this is a pretty simple thing to observe, that as long as you enclose this point charge in there somewhere, if it has 4 electric field lines coming out of it, then you have to have 4 electric field lines coming out of that surface. But it turns out, if we quantify this and turn it into math, this actually gives us Gauss's law. So, the key thing that we need to quantify is, what do we mean by the number of electric field lines going through a surface? Like, what physics quantity do we use to represent this? And we represent this by what is called electric flux. Electric flux. We represent electric flux with a capital Phi subscript E, for whatever reason. Now, if I wanted to be a bit more precise, I would say that electric flux measures the amount of electric field going through a surface. Because electric field lines aren't like an actual physical thing that is present. It's just very dependent on how we actually decide to draw it. Okay, so the mathematical definition of electric flux is the surface integral of the electric field dot n hat, the normal unit normal vector of every single piece of area. Now, that's really complicated. Like, why is there an n hat? What is this? Why is there a dot product? And you might also see it written as the surface integral over E dot dA. Why is A a vector? What does it even mean? So, first, let's actually talk about that. And let's talk about electric flux first in the simplest of cases before we start having to deal with the integrals. And that is, we have a flat plane and a constant electric field. So what's the electric flux in this case? So let's draw this out. We're gonna have some lines. I'm gonna make it a little smaller. So let's say we have some constant electric field. So we have an electric field, and we're gonna just say it is some constant E, constant magnitude E, times I hat. Then, if we have an area A, and this is a flat plane rectangle with area A, then we define this to have an electric flux of A times E. And this kind of makes sense. If we double the electric field strength, then we have twice the amount of electric field lines going through the rectangle, so we should have twice the electric flux, and we do. alternatively, if we double the area, we should get double the electric flux, because now there's twice as much area and twice as many lines still going through, and we can see that that's still true. So, that's great. Next, we can see that the units of electric flux are going to be the units of area, which is meters squared, times the units of electric field, which is newtons per coulomb. So, the units of electric flux are newtons per coulomb times meters squared. Okay. Now, it turns out that just giving the area and giving the electric field strength actually isn't enough to determine what the electric flux is. Because the thing is, rectangles can be tilted. And if you tilt a rectangle, the amount of electric field lines going through it changes. So somehow we need to incorporate the angle into play. So I'm going to draw that real quick. Draw a new diagram. And now this is going to be a side view, because that's easier to draw and do math on. So let's say we have this, and then we have this. Now, so we need to introduce the orientation of the plane into this. So we introduce it by introducing the unit normal vector, n hat. So the unit normal vector n hat is the vector that is perpendicular to the rectangle and is also a unit vector. And so this describes the orientation of the rectangle for us. In the most extreme case, if the n hat is perpendicular to the electric field, so if we have n hat pointing this way, then that means the rectangle is parallel to the electric field lines, which means that no electric field is going through the area. And if no electric field is going through, then that means we should get that the electric flux is going to be 0. So if we want to calculate the electric flux of a tilted area, then what matters ultimately is what its height is compared to the plane perpendicular to the electric field lines. So to figure out what the height is, if there's an angle theta between this perpendicular plane and the original rectangle, then the area of this shadow is going to be a cosine of theta by right triangle stuff. So then, after that, we can safely multiply by the electric field strength to get EA cosine theta. And then, if we run this for theta equals 0 and theta equals 90 degrees, at theta equals 0, we can see that cosine of 0 is equal to 1, so we get EA, which is what we have before, which is what we would expect. And if theta is equal to 90 degrees, then we get cosine of 90 degrees equals 0, so then we get that it's completely flat, which also matches, because that corresponds to this case right here. Now, having it in terms of theta is a little awkward because we want to work with n hat, because n hat is the variable we introduced. So we can move this theta. This theta is the same angle as this theta here. So we get that EA cosine of theta is actually the same as A times the dot product of the electric field vector and the unit normal vector, n hat. So this is where the dot product comes from, and this is where the n hat comes from. The dot product n hat is to incorporate the orientation of the rectangle into play. Sometimes, if a math person is feeling like, or a physics person, if they really feel like they want to simplify things even further or write even less, they'll merge these two things together into a single vector, a hat. Not a hat, a vector. And instead write e vector dot a vector. So a vector is just defined to be n hat times A. So it's the vector for a rectangle. It's the vector that is perpendicular to its surface, and its magnitude is going to be the area of the rectangle. Okay, so this is how you find the electric flux for a flat plane rectangle in a constant electric field. It is defined by electric flux equals E dot A. So how do you deal with more complicated situations? How do you deal with weird blobs and shapes? Like, let's say we have a dolphin. Let's say we have a dolphin as our surface, and we want to figure out what is the electric flux going out of the dolphin. And we have that the electric field is different for every single point on the dolphin. So how do we find the electric flux in a situation like this? Well, first, we split it into a bunch of different flat planes, because we know how to deal with flat planes. Second, we pretend that the electric field on a flat plane is constant, even though it might be changing. And third, we calculate the electric flux for every single one of these little triangles. For a triangle, we figure out what the unit normal vector is, we figure out the area, we get the electric field, and then we calculate the electric flux for a tiny little triangle to be E dot n hat delta A, where we're going to have delta A represent the area of one of these tiny triangles. So we do that across all of the triangles across this surface, and then we add up all of these little tiny electric fluxes to get the total electric flux across the entire surface. Now, this only gives us an approximation, and if we want to get a super precise, super accurate result, we would want to make the number of little triangles we split it to bigger and bigger and bigger, all the way out to infinity. So in the infinite case, we, instead of writing it as a sigma sum and using delta, we introduce the integral into play. So it's an integral over the entire surface of the dolphin. We take the integral of these little pieces of electric flux. And these little pieces of electric flux are, if you have a little piece, a little area of the surface area, so if we have a little dA, then we find the electric field across this area. We find the unit normal vector for this tiny area, and we find the area of this little tiny area. And then we do the E dot n hat dA. So this gives us what this gives us a tiny little electric flux that this area contributes. And so if we want to get the total electric flux, we take the integral of it across the entire surface. So this gives us the total electric flux. So that's what the entire statement of electric flux equals the double integral, the surface integral of E dot n hat dA means, or the surface integral of E dot dA vector. So that's what it mathematically means. Now, to solidify our understanding a bit and check to make sure you understand, we're going to do an example problem. So, consider the triangular prism at left. The electric field for every point on a face is constant and has the value indicated. What is the electric flux through the surface? So to find the electric flux through the surface, we find the electric flux for each of the 5 faces and then add them all up. So let's just go one by one. So for the left face, so flux E of left face. So this is going to be equal to, since it's a flat face, we don't need to do any integral stuff. This is going to just be E n hat E dot n hat dA well, not dA, A, which is going to be equal to, so let's figure out what n hat is. N hat is going to be, well, we actually have a bit of a decision here, because there are two unit normal vectors that are perpendicular to this surface. There's one that goes into the triangular prism and one that goes out of the triangular prism. The convention is to take the unit normal vector that goes out of the triangular prism. So in that case, that's negative I hat. So plugging that in, we also have that the area of this face is going to be 1 meter times 1 meter equals 1 meter squared. So then plugging it all in, we get 2 I hat times negative I hat, well, dot negative I hat times 1 meter squared, which is equal to negative 2 newtons per coulomb meter squared. So that gives us the flux of the left face. So now let's do the flux of bottom face. So this is equal to the electric field dot n hat A. So in this case, n hat is going to be negative j hat, is going to be the unit normal vector in this case, and the area is still 1, so then this becomes negative I hat plus 3j hat dot negative j hat times 1, which is equal to negative 3j. Well, negative 3 newtons per coulomb meter squared. So notice that these have been negative fluxes. That just means that the net electric field is going inwards in these cases. Okay, so 2 done, 3 to go. Let's speed through these more quickly. Of the front face. So the front face, the unit normal vector is going to be k hat. The back face, the unit normal vector is going to be negative k hat. Either way, it's actually symmetric. In this case, they were defined symmetrically, so then E dot n hat A is going to end up being k hat dot k hat times the area, which is 1 times 1 times 1/2 because there's a triangle. So this becomes positive 1/2 newtons per coulomb meter squared. And so by symmetry, we get the back face to be equal to plus 1/2 newtons per coulomb meter squared as well. And finally, the diagonal face so this time the n hat is a little more complicated, although the electric field is just 3I hat. The n hat in this case is going to be diagonally out. It's not going to have a k component because this this plane doesn't change in the k direction. So instead, it's going to be along the direction of I hat plus j hat. But this isn't a unit vector. To make it a unit vector, we should divide by the magnitude of I hat plus j hat, which is square root of 2. So we just divide by square root of 2. And that gives us a unit normal vector. So let's multiply by the unit normal vector. So it's dot I hat plus j hat over square root of 2. And then let's multiply by the area. So by Pythagorean theorem, this is of length square root of 2. So this is 1 meter, square root of 2 meters. So then the area is just square root of 2. So we get that this is equal to positive 3 newtons per coulomb meter squared. So putting it all together, we get that the total electric flux is equal to the sum of all of these, which is going to be minus 2, minus 3, plus 1/2, plus 1/2, plus 3, which is going to be equal to negative 1 newtons per coulomb meter squared. So that's our final answer. Alright. Cool. Next, we can talk about Gauss's law. And now that we've actually defined what electric fluxes and gotten comfortable with it, Gauss's law is actually really simple. It's just the statement that the electric flux of a closed surface, so if we have some closed surface and we have some electric flux coming out of it, it's actually equal to the charge enclosed over epsilon 0. So the charge enclosed is just how much charge is inside of this closed surface, and epsilon 0 is a constant known as the permittivity of free space, and its value is 8.854 times 10 to the negative 12th, and its units are, well, you can use a lot of units, but the most common ones is farads per meter. So, and that's it. That's the entirety of Gauss's law. Most often, you'll see it written as the surface integral of E dot dA vector equals Q enclosed over epsilon 0. But really, this is just electric flux. So yeah, that's Gauss's law. And so what this means is, if we know what the electric flux is, we can figure out what the charge enclosed is. So that means, for this problem, we figured out that the electric flux through the surface was negative 1 newtons per coulomb times meter squared. So that means the charge enclosed, we know that by Gauss's law, this is equal to Q enc over epsilon 0. So we have that Q enc is equal to the electric flux times epsilon 0, which means that it's equal to negative 1 times 8.854 e to the negative 12th, which means that it's equal to, not e to the negative 12th, times 10 to the negative 12th, which means that this is negative 8.854 times 10 to the negative 12 coulombs is the charge enclosed. So that's great. Okay, so one last thing about Gauss's law before we finish with this video is that Gauss's law and Coulomb's law are actually equivalent. They're actually the same. And so we're going to show how we can derive Coulomb's law from Gauss's law, and it'll also be a good example of how we can use Gauss's law. So we're going to just derive Coulomb's law from Gauss's law using Gauss's law and also a bunch of symmetry. So let's draw an electric charge. It's in 3 dimensions, so we're going to actually draw the 3 dimensions this time. And consider a sphere with radius r. So it has radius r. Now, the electric field on the surface of a sphere is going to be radially outward. And the magnitude of the electric field is going to be the same on this sphere. The magnitude of the electric field, by symmetry, should only depend on the distance from the charge to the point. Because it should be a radially symmetric situation. It would be kind of strange if, for some reason, the west side, the left side, had a stronger magnitude of force than the right side. So to denote this electric field magnitude, I'm going to use E of R to denote this magnitude, because all that this magnitude depends on is the radius. Okay, cool. Now with this setup, let's apply Gauss's law. So Gauss's law tells us that the electric flux is equal to Q enclosed over epsilon 0. So let's figure out what the electric flux through this sphere is. Okay, so this, it's equal to the surface integral of E dot n hat dA. So let's look at a tiny plot dA. look at n hat. N hat is radially outward, because the normal vector to a surface of a sphere is going to be radially outward, which also means that the electric field vector is also in the same direction. So we get that for this point, we get that the electric field vector is going to be the magnitude, E of r, times the unit normal vector. So what we get is that this is equal to the surface integral of E of r times n hat dot n hat dA. Now n hat dot n hat is just going to be 1. So this gives us the surface integral of E of r times dA. Now E of r is a constant, so that means we can pull it out. So we get E of r is times the integral s of dA. Now what is the surface integral of dA? Well, what this is saying is across the entire surface, we take the area of every single little piece of the surface and then add it all together. And if we do that, what we end up getting is the entire surface area. So this quantity is just the surface area. Okay, so scrolling down, we can write that E of r times the surface area. The surface area of a sphere is 4 pi r squared. Cool. So next, we found what the electric flux is. Let's plug it into Gauss's equation, Gauss's law, to get that E of r times 4 pi r squared is equal to the charge enclosed over epsilon 0, or in other words, the strength, the magnitude of the electric field is going to be 1 over 4 pi epsilon 0 times 1 over r squared times q enclosed, which is exactly Coulomb's law. Alright, that's all for this video. Hope you enjoyed. If you learned something from this, please like the video. If you have any comments to say, or especially if I messed something up somewhere, please comment down below. And finally, if you want to watch more videos like this and support what I do, subscribe.